Hello, hello. There we go. Good morning, everyone. Thank you to all of those who are slowly coming in after last night's party. And we're going to keep it kind of light this morning. We're talking about space and AI and how we're leveraging space technology to explore for minerals. So this is my favorite astronaut. This is Buzz Aldrin standing on the moon in the summer of 1969. And he is not the first man on the moon, but he was the first man to deploy a geoscientific instrument on the moon. So he's the first guy who collected any geoscience data on the moon. And what he's deploying there is a passive seismic instrument, and that passive seismic data was live streamed back to Earth. And this is kind of an origin story for Fleet, where we do similar things with passive seismic data on Earth now. So this is how Fleet came about. This is how we thought about doing what we do on Earth today. And this is the first seismogram. So this is the first geoscience data that anyone has ever collected on something off of Earth. And Fleet is very proud that in 2026, we're going to be sending our own seismic instrument to the moon, and we're going to be collecting our own seismic data. We're going to be recreating this for NASA, and we're going to be looking for water ice on the south pole of the moon. We also have a grant from NASA to develop a lunar gravimeter, and I'll actually show you some testing we've done with that later on in the slide. But we are actively building geoscience, geophysics instruments to collect data on the moon. But we're not here to talk about the moon today. We're here to talk about Earth. And we're here to talk about our mission, which is to accelerate the discovery of minerals. Now, I know there's not a lot of you here right now, but raise your hand if you want to find your next mineral deposit slower. Who wants to explore slower? Does anyone want to take more time to find your next mineral deposit? And I don't think so. I think we're all aligned that we really need to do this quicker, and for a couple of reasons. We want to do this quicker because it is more efficient. It allows us to deploy our capital in a more efficient way and find these things cheaper. I mean, the market's all over the show. It was up yesterday, it's down today. How are you going to deploy that capital quicker? And it's by exploring quicker. It also allows us to get more of these minerals into the pipeline quicker, which we know we need for the future of humanity. So Fleet is here to collect insightful data, reliable data, but most importantly, rapid data. So what is a space tech company doing at a mineral conference? Well, we build our own satellites. As I've said, we build our own geophysical sensors. We build our own software to process data, to host our AI models, to provide some of these insights. And we're deploying that in the mineral exploration space because there's quite a lot of parallels between exploring in northern Canada or far rural Mexico or up the side of a mountain 6 kilometers in Chile. There's a lot of parallels between that and exploring somewhere like the moon. And one of the things we're most proud of, I mean, obviously we have all the shiny satellites and we have amazing sensors and we're building gravimeters to go to the moon, but it's really our geoscience team. So Fleet has somewhere over 30 geoscientists who are focused on processing data, helping our clients interpret that data, looking at AI models, coding AI models, and it's this large geoscience team that really is the backbone of all this amazing tech that I'm going to be showing you today. So this is what we're going to talk about. We're going to look at ambient noise tomography, which is a fancy way of passive seismic. We're going to look at mineral systems mapping on a very large scale. And to do that, we're going to go to Eastern Australia. And then we're going to have a far smaller scale case study, high-resolution data in Silver Mountain, Arizona, show you the breadth of scale that we can deploy ambient noise tomography at. We're then going to have a look at some of our AI models and how they can help predict porphyry mineralization. And lastly, just some of our future developments in multiphysics. How do we combine gravity, electrical methods, seismic methods? How do we combine all these? What research are we doing to combine all of these methods to provide you guys with more insightful data? So this is how we collect ambient noise tomography. It's in the name. We're listening to the hum of the earth, the whispers in the ground, things that get created from ocean noise, things that get created from mills and railway lines and cities. We don't use explosive sources. We're just listening to the background noise of the earth. That is our source. And so this is obviously a very environmentally safe method, very little disturbance. A brief history of this technique. It's not new necessarily. It's an academic technique that's been used since the late 50s. But really only in the early 2000s have people in California, they showed if you looked at this background noise, you could actually process it in a way that mapped geology. And now we are in the 2020s, and Fleet is deploying these real-time surveys where we're putting a satellite modem on every single one of our geophones, and we're live streaming that data through our satellites that we produce into the cloud for rapid processing and insights that we deliver to you guys. And so this is an example of just showing you exactly what we collect. So station A up top is collecting noise. Station B is collecting noise. But that's not our geophysical signal. Our geophysical signal is here at the bottom. It's this correlation. It's how is station A and station B, how similar are they seeing that background noise? And we'll normally collect that data for a few days. You can see here already after 45 minutes of stacking, we're already getting a signal. And so that on the bottom is our geophysical signal. But that is only connecting 2 stations. This array has 100 stations. And actually what we do is we connect every station to every other station. And that means with 100 stations, we get close to 5,000 connections. We're also collecting various frequencies. This is a broadband solution. And so you can see there 0.8 hertz, roughly at about a kilometer depth, because frequency equals depth in ambient noise tomography. But if we we connect all those stations just to the one in the bottom left, and we lay them out properly, you can see it looks like there's energy going through the array. And that's actually the velocity of the ground. So we're seeing that velocity, but that's only connecting to that one station in the bottom. We obviously do that for every station. And that's how we figure out what the velocity of the subsurface is. It's using various frequencies and connecting up all these stations. Basic high school physics, the lag time signal that we collected, the distance that the stations are apart, distance time gives you the velocity. So that's what we're collecting. As Fleet, we're collecting, understanding the velocity structure of the ground. So I'll be showing you a lot of velocity images. But specifically what Fleet does, how we do this, because we're live streaming this through our satellite network, but it starts with our sensor. It starts with designing a specific geophone, 2 hertz, a lower frequency geophone, but that's very sensitive. That's just designed to collect ambient noise data. We then connect every single sensor. So if we put out 100 sensors, every one is connected to the satellite. Put out 200 sensors, every one of those sensors is live streaming data through a satellite into a cloud processing platform. And that data is then, we can control the quality of that data because it's being processed in real time. If there's a problem with a sensor or a group of sensors, we can send a field crew out and we can fix that. So a lot of the data connection is actually for data quality control. We have a passive source. We don't control the noise sources, and so we monitor those noise sources. We make sure we have good frequency coverage so that the quality of data that we provide you is very high. As we go later in the talk, we'll be talking about AI, but AI hates noise in data. It likes to quantify the error, and by ensuring that you have high quality data in the beginning, we're able to use the AI more effectively as well. So as I said, we live stream this data, and it means we get a look at the data before it's finally processed. So by the time the survey is actually done and we see enough signal, we can then process and give you a final geophysical model in less than 48 hours. And that'll be constrained with whatever geology or drill hole data you give us or other geophysics. And so we're talking about giving you doing a geophysical survey, laying out the nodes, collecting the data, processing the model in something like 7 to 10 days. You get a geophysical data set from time of deployment to final model. And so that's really rapid. And that's what Fleet's all about, is high quality data really rapidly. This just shows you I'm not just waving my arms. We have a lot of high-tech science and algorithms and software development that we've put into creating this workflow for ambient noise tomography. And we do some unique things here, employing large cloud compute. We spend a lot of money with Amazon to use the commercial tools that are available to the tech industry to really drive these models to you very quickly. So we're going to look at our first case study today, and this area is in the eastern part of Australia, in New South Wales, and it's part of the Lachlan Origin. Is a failed subduction zone, and there's a whole stack of these volcanic arcs that occur here in New South Wales, and we're going to have a look at one of these volcanic arcs, the Juni Narromine Belt. And there's an explorer there called Inflection Resources, and they've recently got $150 million from AngloGold Ashanti. So they have AngloGold Ashanti money, and they staked out 7,000 square kilometers of licenses undercover. So you can see there are a lot of mines here in areas that are not covered, but it takes a very brave explorer to go exploring under 400 to 600 meters of post-mineral cover, but that's what Inflection is doing. You can see in the magnetic image there on the right that volcanic arc clearly extends undercover. And so what we're doing with ambient noise tomography is we're trying to explore that region. And so we're going to look at, we're actually just going to look at one survey today. We're going to look at that black survey. It's a very large regional survey that we collected. So here you can see this big survey. 5-kilometer station spacing, so we're trying to look deep. We're looking at mineral system, crustal scale features. We're trying to see how does this whole mineral system stick together. And we laid out all of the geophones, an area of 1,800 square kilometers. That's 150 meters of strike length north to south. We produced a model that goes down to 5 kilometers. You're looking for crustal scale features. You need to look deep. But we did all of that in 3 weeks. Laid out sensors, collected data, processed a model in 3 weeks over 1,800 square kilometers. This really is very, very rapid data. And because of the way we process the data, we can obviously provide you with the velocity model, the geophysical model, but there's more behind that model, and things like the confidence and the sensitivity of the data. These are really important metrics to the people who are going to interpret your model, but they're even more important to things like AI models. If you can quantify the error in your inversion, how confident the inversion is on that velocity cell, that really helps the AI model understand that velocity cell and interpret it computationally. The other thing that we do is we monitor these frequencies. It's a very large survey, and so we're monitoring where these frequencies are coming from, where these noise sources are coming from in real time. And there are certain towns around the array, and those towns are providing most of the higher frequency noise that we're getting in the array. But looking at the actual models, you can see there's a range of depth slices here, from about 4.5 kilometers to 750 meters depths. So we're trying to figure out what is going on with this mineral system. And you can very clearly see there's a north-northwest trending, large-scale structural feature. And that's really the structural feature that Inflection was staking their ground on, right? So that's that big structural feature, and we can see that feature here. What's interesting in the image here at 4.5 Ks is you get some of these cross structures, and we're going to look at those cross structures and what some of those structures mean later on. But what's interesting is when you see some of these velocity anomalies in the near surface, something like a felsic intrusion would be high velocity in the background of a very old, this is 450 million year old rocks, a very old volcanic arc. So those are very interesting that you see these high velocity anomalies, which could be intrusions coming off of a deep structural feature. In Australia, the exploration community is very lucky. They have access to really good public data. So the New South Wales government has a 1 kilometer airborne gravity. It's actually a Falcon data set, which we downloaded and did a 3D density model. And because this is a volcanic arc, you expect those densities to be quite high. So that density isosurface is 2.7 grams per cc. The velocity isosurface is quite high as well at 3.1. And what we're trying to show here is that where you get high velocities, you're actually getting low densities. And when we look at some of the anomalies and think about the petrophysics of high velocity and low density, we're now seeing that we're getting a high velocity pod. You can clearly see this big crustal scale feature now. And now you're getting this high velocity pod coming out of this crustal scale feature, intruding into what the gravity says is a low density zone. So we're thinking that's probably going to be something that is at least intermediate or felsic in composition. And this is a really good place to go exploring for porphyries. And so remember, this is very wide scale data, 5 kilometer spacing, but we're able to provide these sorts of insights in 3 weeks over a huge area. Another area down to the south, I said we're going to come back to these cross-cutting structures. Inflection and Anglo Gold, they went and they drilled a wildcat hole down in the south, right on one of those structures. And you can see there's this low velocity zone, maybe a feeder zone, something that fluids could come up. And in the near surface, there's a high velocity zone. They drilled that. Oh, what's going on there? And you can see in this velocity image right on the edge of a sort of high velocity area. And they found really good alteration. They found copper mineralization, and it's an area that they're going to go exploring even more. So, something that took us 3 weeks to create, you've got a whole district that's now, you're understanding the mineral system, you're understanding which parts of that district are more prospective than others, and you can go deploy your capital effectively to go and explore those areas. So now we're going to come right back down to the prospect scale. We're going to have a look at a small survey we did for a junior miner in Arizona called Eagle Mountain Mining. A good friend of mine, Brian Paul, works there. I think he now works at BHP. But Eagle Mountain have an interesting project on kind of the confluence between a big VMS corridor that goes just north of Phoenix, and you can see they're in a very nice real estate with BHP and Freeport all around them, and a VMS corridor that goes up to the north. These images all come from press releases that Eagle Mountain put out on July the 9th and the 1st of October. So this is work we did last year. But you can see there on the left-hand side, on the right-hand side, sorry, you can see that's the velocity model, and we're highlighting 2 high-velocity targets in the north there, and you can see what the geology looks like. There's an area of cover, there's a large-scale fault that goes through there, and they've had some alteration where they have rocks that are sticking out of that cover. And so that's lining up quite nicely with what the ambient noise tomography is showing, and you can see here from this drill hole, in the near surface, it's only about 150 meters, you can see you're in the right sort of geology, in the right sort of rock. You can see you've got good chlorite alteration, etc., in the kind of propylitic zone of that area. So this is a schematic interpretation of what the ambient noise tomography data is showing you. And you can see there we're picking up some structural zones. We're mapping the cover sequences quite nicely. But most importantly, we've got these offset high velocity targets that are again lining up quite nicely with what's happening at that silver dollar zone in the near surface. If we look at other geophysical data sets, we can see those high velocity targets. On the mag, we've got a classic porphyry response of a low mag ring in the southern one. In the northern one, you probably wouldn't pick that out of the mag. In the gravity, again, in the southern one, you've got that low density, maybe felsic geology in this volcanic package. And so that southern target looks like it's lining up in various data sets. If you think of the petrophysics in the mag, this high temperature fluids are destroying all the magnetite, and that's why you've got a mag low. So looking at some cross sections through here again, and also looking at doing a 3D magnetic inversion and how that relates to the ambient noise tomography, you can clearly see between these low mag targets and these high velocities, these are areas that Silver Mountain is going to be looking at in the future. Is going to be, once they have a bit more money, that they're going to be drilling into these targets to try and figure out what are those rocks at depth, what do those rocks look like below that silver dollar zone where they see some good alteration in the near surface. So this was, again, a very rapid survey that we did for them. And you can see, obviously terrain that's very similar to terrain that you get here in Mexico is just across the border. But things like terrain really don't bother the ambient noise tomography survey too much. We can correct for it. It's really on the deployment team whether they can get up and down these big mountains that we're seeing. So now we're moving to our last case study, and this is going to be a short look at some AI modeling that we did for a tier 1 mining company with a large porphyry deposit that they're busy drilling out. This will become a mine, but they were looking for a method to understand where the edges of their mineralization were and possibly find new mineralization around a larger district that they've got around this resource that they're busy drilling out. And so we did a lot of ambient noise tomography work for them. They had some magnetic data that they had collected. There was some hyperspectral data and a very large drilling data set. They provided us with access to 10,000 assays. And so that was the data that we input into our AI model. There was a foundation model that we created for this district first, just using sort of general data, but we then had this specific data that we were adding to that foundation model in the zone. And something that we did that not a lot of other AI companies do is we were very aggressive in how we trained this model. We had a lot of data to train it on, these 10,000 assays. So we literally split it in half. Most people will train on 80% of the data and only validate with 20. We trained on 50% and validated on 50%. We also spatially separated the training and the validation data. A lot of AI companies will randomly select the training and validation data so that those data points are close together. But that's not how we were going to deploy this model. We were going to deploy this model spatially separate from where we trained it. So we were trying to train it and validate it to see if it worked using spatially separate data. And so we literally north-south, there are data points here in the south that are maybe 5 kilometers away from data points in the north. And we were trying to be very aggressive in how we did this validation. So the results I'm going to show you are us being very aggressive and trying to really actually understand the validity of our models and not just trying to put some nice numbers together. We could have had much nicer numbers if we were less aggressive in our validation. And so we were looking to try and predict any copper above 0.18%. And yes, that's a very low cutoff grade. But that was the cutoff grade for this very large project. And they were like, let's see if we can predict these grade shells of 0.18%. And so 85% of the assays they provided us were above 0.18%. And so 85% of those assays were positive. And so we ended up predicting 71% of those positive assays. And that's called our recall. Now, we could have had that higher, but what was really interesting is that actually 91% of our predictions were correct. So our accuracy was 91%. So what that means is we can actually tune the accuracy in the recall. We could have had far more of those positive assays that we would have predicted, but we would have also predicted far more false positives. And there's no quicker way to kill a project than to go drilling false positives. So we specifically tuned that to kind of keep it, very high accuracy, but keep that recall at a point where we're not providing too many false positives. But in terms of what we're able to provide, that means that using 5,000 assays, we were able to predict where 71% of the other 5,000 assays where they would have found copper above 0.18%. It also means that we were 91% correct in predicting exactly where that grade shell was going to be, positive and negative. And I gave you perspective on how aggressive we were with training our model. So I think those numbers are really quite impressive given how aggressive our validation program was. So now we'll quickly look at some future developments. As I mentioned earlier, we have got a a grant from NASA to develop a lunar gravimeter. And so this is actually us field testing out in Australia. A MEMS-based gravimeter uses a gravity system on a chip. And we were field testing these against a Simtrex CG5 to understand how much development we needed to put into this. There you go, you can see the CG5 there as well. And so we did these field tests in 2024, and we'll be working with NASA to kind of bench test this, figure out how do we get a gravimeter up to the moon. We're also working, we're at very early stages of looking at doing R&D on a no-dig magnetotelluric system. How can we collect magnetotellurics data, which is also very important in porphyry and ICG exploration? How do we develop a system that is far easier to deploy, is cheaper to deploy, and so we actually collect more data? So Fleet is actively doing sensor R&D, and obviously through our AI, we're doing software R&D. And in terms of just concluding, we've seen how ANT is used at multiple scales, at very large, 1,800 square kilometers at a time, or then, just at a prospect scale. How can we help explorers figure out where to go drilling? We're integrating very well with multiple other methods of geophysics. So ambient noise tomography sounds all exotic, but it's been around for a while. It plays nicely with the other data sets that you already have. We've been deploying our AI models for about a year, and we've had a lot of successful clients who've been using these to help them understand more about their geology and their mineralization. But really, I'm just very excited that we will have a seismometer on the moon in 2026. And it's crazy that this is a real picture. This is not an AI-generated picture. It was the Artemis 1 mission that flew around the moon. And if you think about it, we've only ever explored those two tiny little rocks over there. That's the whole history of human existence on those two little specks over there. So we're very excited to take that further as Fleet. Thank you to you for listening. Thank you to Inflection Resources and Eagle Mountain Mining, and to Doug and his team for putting on a wonderful conference.